And now it's time for our special guest. Joining us, another person from RIT. I really feel like Dr. Brian Koberlein is sending us a whole bunch of his coworkers, but we've got Jeyhan Kartaltepe from RIT. Jan, welcome to the Weekly Space Hangout.
Hi, thanks. Thanks for having me.
All right, so let people know who you are and what you do.
Sure. So I'm an astronomer at RIT. I'm an assistant professor. It's my third year or so here, and I'm loving it so far. I work on extragalactic astronomy.
And you're joining us because you're talking about or you're working on the Cosmic Evolution Early Release Science Survey. CEERS, is that the way to describe it? Is that the way to say it? Is that right? CEERS?
Yes, that's right. Like CEERS.
Yeah.
Yeah.
I can see you're starting to lose your connection a bit, but we'll see what we can do.
Oh, okay.
So what is CEERS?
Yeah, so this is one of the early release science programs on the James Webb Space Telescope. And so the idea is there was a call for some projects that are going to make use of various instruments in different ways. And the idea is this data will be immediately available to the public so that anybody can play with it, try it out, learn the ins and outs of data from the Webb telescope, and then be prepared when it comes time to submit their own proposals for the next cycle.
So could you compare the survey that you're going to be working on with other surveys that maybe people are familiar with? Like, we've talked quite a bit about the Sloan Digital Sky Survey, and then we've talked about sort of special surveys that were done, things like the Hubble Deep Field. What is the CEERS going to do, and how will it be sort of similar and different from other surveys out there?
Sure. So I've worked on a number of these large extragalactic deep surveys. So the Hubble Deep Field is one that I'm familiar with. I've worked on Cosmos, which is a large one with Hubble, Candles, which is another large one with Hubble. So it'll be a little bit similar. So we're using one of the Candles fields. So this is the EGS, the extended growth strip, because it's optimally viewable at the time period we're looking at. But the idea is we're going to use the Webb instruments. So it'll be both an imaging survey in the near and mid infrared, but also a spectroscopic survey with NIRSPEC, the near infrared camera.
And we've talked about James Webb ad nauseum here on the Weekly Space Hangout for many weeks. This Week in Webb, I think, is maybe its alternate name after This Week in Musk. But
James Waite Space Telescope.
James Waite Space Telescope. And of course, we recently reported that it's been pushed back to 2019. So sorry about that. I'm sorry. Did you have a career that depended on this telescope going to space? Because
at this point, I've waited almost my entire life for this thing to launch. So what's another 6 months?
Yeah, and spent all your money. But I mean, James Webb is going to be a monster compared to the space telescopes that are out there right now and the ground surveys that are done. So give us a comparison of just like how far are you going to be able to push out to be able to see?
Yeah, so we're hoping to identify a handful, sort of 10, 20 of some of the first galaxies to have formed in the universe. So this would be things at redshifts 10, 11, 12. That's sort of the goal and what we designed the survey around. But of course, in addition to that, we'll have thousands of galaxies across a whole range of redshifts that we can study in great detail.
So what would that compare? Like, for those of us who don't speak Redshift, not you, Paul, what is a 10, 11, 12 in terms of like age after the Big Bang?
Yeah, I should have that number in my head.
Okay, fine, Paul.
100 million years. Maybe Paul has a better number.
Yeah. A couple of 100 million years?
Yeah.
I'm just Google searching it right now.
Yeah.
Where you pulled up the cosmology calculator.
Yeah. That's calculator.
It's funny, we muggles need that we need to know it in light years and in time after the Big Bang. But I know that for astronomers, you want to talk in kiloparsecs and redshift. So
my go-to. So I usually work on lower redshift things, and so redshift of 1 is roughly half the age of the universe, and so that's sort of a good number I keep in my head. Redshift of 2 is something like a few billion years after the Big Bang. So this is kind of my first foray into the really, really high red universe.
But so, I mean, I know when we think of like some of those oldest, most distant galaxies found by the Hubble Space Telescope, they are using, say, gravitational lensing to do this bank shot view, essentially use galactic clusters as natural telescopes to be able to kind of get right out to the edge, but you need that special lineup.
Right.
But Webb is just going to do this brute force, right? It's just going to go right out.
It's a larger telescope. It's more sensitive. It's optimized at these wavelengths. So lensing has sort of been Hubble's way of getting at the very edge of what the James Webb will be able to do. But James Webb will clean up once it launches. And
so then what will you expect to see out that far to the edge of the observable universe?
Yeah, so we'll see some of the earliest galaxies to have formed, and not only that, we'll be able to study their properties. So once these objects are identified, we can then go back and get spectra of those galaxies. And that's something that's really impossible from the ground, but you need spectra to give us information about the actual physical properties, to confirm their redshifts, to measure their masses, to measure their star formation rates and other things. So we can sort of piece together how those first galaxies formed that early and got to be as massive as they are.
And what are the big unsolved questions that you have? If you could get that data right now and try and get some answers, what are some questions that you would really like to know the answer to?
So knowing how many of them there are and at what periods of time after the Big Bang is important, because we want to understand how quickly they formed and how they were able to reionize the universe. So that'll be our first real statistical handle of that time period. Instead of just sort of one or two objects, we'll have a good number of them. And we want to study their black holes. It feels like every few weeks there's a new distance record for a massive black hole that's been found. And every time it's, how did this thing form so quickly, so early on? So those will be some of the questions we'll be looking at.
Yeah, I mean, even just, I guess a couple of weeks ago, one of the last stories that we had be able to report on was that a really massive black hole was found right at much farther out than anyone ever would have expected to have already formed. Mm-hmm. I mean, so what are some of those other sort of, and for those people who kind of don't know what like the reionization period is, like that, just those first moments, those first stars, and we just don't know still what happened, what it was like right after the Big Bang.
I mean, those very first stars would have been made up of almost completely out of hydrogen. So their properties would be very different from stars today. And so what we know right now is all theoretical. And so being able to understand that process, to see how quickly they were able to form and how massive galaxies were able to get at such an early time when they didn't have the metal-rich environment that galaxies do today.
And now you mentioned that a lot of this data is going to be out there available on the internet. Where does that, I mean, is that not the case right now with things like Hubble Space Telescope? How is it different from the way some of these other telescopes work?
So there's sort of a range of things. Individual programs that an individual can lead are typically not available to the public until after a year that it's taken. The big legacy surveys, that data is made public immediately. So things like the Hubble Deep Field, the Cosmos Survey, et cetera, that data is made public immediately. But most programs aren't. And so for the James Webb Space Telescope, the first things that will be done, the builders of the telescope and the builders of the instruments have their own guaranteed time programs. Those will not be made public immediately. They have a period of time that only they can use the data. So the only data that will be made publicly available immediately will be these early release science programs. And so they span a wide range of science topics and make use of all the different instruments in various different modes.
Right. I was thinking about like what was happening back with the Rosetta spacecraft. They had several instruments, the NavCam pictures that were released immediately to the public, but the sort of fancier camera images that the scientists got to hold on to and work with before they were able to finally release to the public.
Right. And there's always some PR data, right? That's sort of like a special project. So there will be PR images that are taken right away that are released for people to look at. They're just sort of pretty pictures that aren't really meant to be used as science data.
And I mean, I think one of the things that I really enjoy about surveys is that you kind of don't know what you're going to find out. You don't know what's there. I mean, you still hear people reporting all kinds of interesting stuff about pulsars and supermassive black holes and stuff in, say, the Sloan Digital Sky Survey. We looked at the Sky Survey for this and found unknown stuff. And some of the upcoming projects that I'm most excited about are these surveys, like the Large Synoptic Survey Telescope, various things like that, which are going to just produce a tremendous amount of data about the sky, and that then can then be poured through after the fact for whatever a person is interested in.
Yeah, exactly. So a survey really gives you the opportunity to be able to do that. Because if you think back to what the original science case was for Hubble, so many of the things we talk about now as Hubble's biggest discoveries were not on that list. People didn't know that we'd be probing galaxies as far away as we are, for example, or we'd be discovering these really massive black holes, or we'd be studying exoplanets, right? Those kinds of things didn't even make the list.
How far into the future is James Webb booked at this point?
Booked. So these programs are only a portion of the first year, and the proposal deadline for the first cycle of just regular proposals isn't until April. So people have until April to come up with plans for what they want to do with smaller amounts of time on the James Webb Telescope for the first year of its operations. But
I mean, it has a couple of instruments, right? So you sort of get to ride along with whatever is, wherever the telescope is pointed.
Yeah, so there's several different instruments, so both in the near and mid-infrared, and if you plan things right, you can use them simultaneously. So that's something our survey is going to do, is use for example, the imaging camera in the near-infrared while we're taking spectroscopy with the spectroscopic camera, and you can do that simultaneously.
All right, so let's assume that there are no more waits. As everything goes as planned, in 2019, it hops on board its Ariane rocket and goes to space. When will we expect to see the stuff that's coming out from your survey?
So the first 6 months or so after launch will be, getting to orbit, going through commissioning, going through all the initial setup. And so the first real science data will probably be taken about 6 months after launch. And then depending on that exact timing, we have a window when our fields will be observable. So I would say somewhere between 6 months to a year after launch is when you'd see the first early release science data, our program and other programs as well.
And what does it mean in this instance to be released immediately? Because, you see like Curiosity takes a picture and an hour later you can download it from the raw data directories for NASA. Is that the sort of immediacy we're talking about here?
Yeah,
or would you guys have to kind of ingest it before it goes out?
The raw data we public immediately, and then the team is going to work on sort of the second level process images, which will then be released on some time scale. But the raw data would just be out there instantly.
That seems like the right way to do it, that you don't know. I mean, sure, the science team is going to be looking for and expecting to see certain things, but getting that out into the public and getting as many eyes as possible being able to look at it. Some of my favorite images, some really interesting stories that we reported on with, as like Curiosity and stuff, are stuff noticed by, in some cases, amateurs, people who are just following along and looking at the data. And some of the great pictures, they're not necessarily so scientific, but they're really wonderful uses of the data to make a really pretty picture. And that's all done by amateurs and people just kind of looking over the shoulders as the science gets done.
Right. And this data, aside from the science, the data will be there for people to test their own pipelines and their own software, so that when they do get their own data, they're ready to go. So they know all of the problems that the data presents, or how to properly calibrate things, how to combine images, etc.
All right. So then, how can people get involved if they want to, if they want to sort of know where to go for when this material is going to be showing up? Where should they go? How can they get involved?
Yeah, so we're going to be putting a website together, as well as a blog for the community to be able to follow what's going along with the survey. That's not up yet. That's one of our plans to do in the nearby future. So people can contact me. They can contact our PI, Steve Finkelstein, at the University of Texas in Austin, so we can let them know about more information. But we will definitely have a web presence, and we'll be releasing information as quickly as we can.
That's great. Well, and good luck with the telescope.
Thank you.
I hope we don't wait anymore, and I hope it actually makes it to orbit safely. And I cannot wait for this to finally come together.
We're all really excited.
All right, thanks for taking the time to speak with us today.
Thank you.
All right, let's move on to the episode. All right, here we go. Hello and welcome to the Weekly Space Hangout for Wednesday, January 8th, 2018. Woo!
Man, I
I'm
haven't
Fraser
seen you guys
Kane.
all year.
Yeah, this is our best episode this year. I'm publisher of Universe Today, and so this week we've got a special episode. We're going to be looking forward to some of the stories that we're going to be expecting to see this year. Joining me, as always, we've got Dr. Morgan Renberg, Director of Scientific Presentation at the Fort Worth Museum of Science and History. Morgan, welcome.
Hey, Fraser. Happy New Year.
Right on. And Dr. Paul M. Sutter, astrophysicist at Ohio State and the host of Ask a Spaceman. Welcome back, Paul.
Hey, how's it going? Thank you.
Now, folks who are listening can't see, but Paul cleaned his blackboard.
I did. So free of chalk.
Yeah.
He may have just taken it away. It's impossible to know. It could just be, a black hole behind him.
It could just be night behind me
Yeah.
in the sub-zero temperatures.
What did it take to get to this reset?
Okay, so it took Coca-Cola. It turns out Coke is actually a halfway decent chalkboard cleaner. And
That was the original plan for the product, I think.
Yeah.
Yes, exactly.
Somebody then got drunk and drank it and said, this tastes pretty good.
And then 3 rounds after that of vinegar and warm water.
Wow. I could see why you
And
only do this once a year.
Will you
Yeah, I
come
know,
clean
it's
my
like-
house?
See, I don't have to wash my hair, but my excuse is if I have an obligation that I want to get out of it, so I'm washing my chalkboard tonight. That's my weekend plans.
All right, well, let's get on in a moment with the sort of all of the big stories that we're looking forward to. But before we do that, I just want to give a big shout out to our beloved partners in this journey around the sun, and that is, of course, the Weekly Space Hangout crew. This is the community of people, really the producers of this show, who join us every week, who jump into the chat that's down there and over on the YouTube, who organize amongst themselves to decide on stories and special guests, and really we couldn't do this without you. So thanks everyone for joining us. Here's to another awesome year. All right, I want to know, well, all right, Morgan, you picked the big one. What is the first thing that you're looking forward to this year?
Oh, it's first both in my mind and in the timeline of the year, because hopefully it'll be happening just in the next few weeks, fingers crossed, and that's the launch of SpaceX's Falcon Heavy rocket for the very first time. And I was sort of poking around this morning, looking at this a little more closely in preparation for the show. And I noticed, and I hadn't, probably most people realize this, but I hadn't realized that this rocket's going to be more powerful than the space shuttle. In fact, it's the biggest rocket.
That's hard.
It's the biggest rocket that will hopefully lift off the Earth since the last Saturn V launched Skylab in the early 1970s. So we're talking about an incredibly huge rocket, but it's going to launch at an incredibly low price. The space shuttle cost about $500 million in like the 80s to launch empty. No astronauts, no science, just put it on the launch pad, shoot it off, $500 million. This is a rocket more powerful than that, that SpaceX is currently on their website selling launches on for $90 million. And it's twice as powerful as the current heaviest lift rocket, the Delta IV Heavy, at 1/3 the cost. And so not only is this going to be the world's largest rocket, it's in some sense going to be the world's cheapest rocket at the same time. And it's for $30 million more than a Falcon 9. You can launch 3 to 4 times as much stuff into space. It's a bargain no matter how you look at it.
Per pound?
I would wager it is. I haven't calculated that out, but it is like 1/3 more expensive than the Falcon 9 for 3 or 4 times as much stuff. So per pound, it's vastly more cost effective than the Falcon 9, which I think would generally already be considered the most cost effective rocket on the market today.
Is any part of the Heavy reusable?
All of it is reusable. That's the
All
cool
of
part.
it.
So it's basically 3 Falcon 9s duct taped together and each piece will
Or
land
literally.
independently on a separate launch pad. And in fact, their plan with the Falcon Heavy is to use up some of the already launched Falcon 9. So they've stockpiled like 20 of these Falcon 9 cores already launched, and they're going to just start putting them together to create these Falcon Heavies, and then they'll be able to reuse those components in that configuration over and over again. Is the general idea?
Yeah, this one, the middle part is new, but the two side boosters are reused, right? And so when this thing takes off, the three parts are going to, as the upper stage disconnects, then the three boosters are going to, fly back down, and they're all going to land on different landing pads all at the same time, or I guess, depending on how long it takes for them to make it back, but within about the same amount of time. Now, the second stage, you said it's all reusable, but not the second stage, right?
Not the second stage, no. Just like the Falcon 9, the second stage is expendable. That's the part that goes into space and actually releases the payload. But the first all three of the first stages will be reusable, just like in the Falcon 9.
The second stage reusable?
There were.
Not on the Falcon Heavy, but that's definitely one of their plans for the BFR, the super successor to the Falcon Heavy, is supposed to be reusable from top to bottom. But I don't think the Falcon Heavy will be.
But I know what you're getting at, Paul. Originally, I think Musk was describing a part of the Falcon Heavy that I'm not exactly sure why, and I'm sure maybe someone will be able to jump into the chat, that with the way it's configured and the way its second stage works, it's more feasible for it to be a reusable second stage as well. And of course, potentially reusable fairing, reusable Dragon capsules. Like, we're getting pretty close to a fully reusable rocket at this point.
I mean, for reusing a second stage, the biggest factor is you're slowing down from much higher speed, and so you need a lot more fuel to burn. But if you have a way more powerful first stage, then you can launch a lighter payload into orbit without having to use much of your second stage. And that opens up the physics possibility for having enough thrust to slow yourself back down. And then it's just a question of whether your hardware can withstand the stresses and the forces necessary to do that, and that your rocket hasn't traveled so far downrange that it's out of reach of any of the landing places. And they have somewhat solved that with the barges.
Well, where are we at right now? So I just showed a video to the audience showing it on the stack. I know they brought it up and then they brought it back down again. Do we know when it's going to launch?
They haven't said exactly yet. So they rolled it out to Launch Pad 39A, which is the same launch pad that NASA used to launch the Apollo moon landings. And they stood it up and basically did all their checks. And then they've sort of tabled it for the moment. So they laid it back down so the wind doesn't blow it over, because they have a secret military launch upcoming. I think it's now supposed to launch on Friday. And that's the last launch on their manifest before the Falcon Heavy. And so once that goes off successfully, they'll be able to start looking for a time. And the next thing they have to do is what's called the static fire. And they basically set the whole rocket up and bolt it to the ground. And they fire all the engines. And they go through all the phases of through liftoff, where they fuel it, they disconnect all the external. They basically simulate the whole thing all the way up to the rocket firing and turning on. And then it burns for a while. And they show that the engines work, that the whole process works. And once that's done, they can stand it up and do the rest of and launch it.
Because the Falcon Heavy is a new one, or is that the standard operating procedure for every launch?
That's the standard operating procedure. Usually when they make the engines, they fire them like at the test facility, and then they often fire them, although I don't think they have to fire them, on the main launch pad as well. And that's just so that, and if you remember actually 2 years ago now, in 2016, at the end of 2016, they had an explosion. Mm-hmm. And that was when they were fueling it up for one of these tests.
So let's talk about the payload.
Yeah, so the payload is going to consist of one late-year Tesla Roadster playing Space
Cherry
Odyssey
red.
inside of a Dragon capsule, and they will be launching that. Originally, Musk had claimed he was going to launch it to Mars, and then for a variety of reasons, they've backed down from that a little bit, and are now going to be putting it into a solar orbit with enough distance that it'll cross the Martian orbit. And so they'll put it in an elongated orbit that'll take it all the way out past Mars. And I don't know how long with that big Tesla battery in there you can run the car radio. But presumably through liftoff, it will continue blasting the song.
I wonder if they've paid for the license.
That's a good question. Maybe they just got a premium Spotify.
Yeah, just play premium Spotify.
Satellite radio.
Well, if you've got premium Spotify, then you can store it on the device, and in this case, the device is the Tesla, right? So it would work. But yeah, that would be the problem is that without any a third stage, some kind of final rocket, you can't actually go into a proper orbit around Mars unless you do an aerobrake. And trying to aerobrake the car into the atmosphere of Mars is a dangerous idea. So and I mean they didn't. It sounds like putting this car on the rocket was a kind of last-minute decision. What do you think, though, about putting a car as opposed to letting other people put spacecraft that could go out into space? Like, doesn't that feel like a huge opportunity lost?
Oh, Musk has been very careful in, I'd say, the last 6 months to really, really, really tamp down expectations for this launch. This is the first launch of a new rocket system. Those almost never go well. And he has said on Twitter that he'll count it as a success if it gets high enough off the launch pad that they don't have to rebuild the launch pad after it explodes. And so, at least publicly, they're not offering a lot of confidence that this is going to work. Yeah. And so I think there wouldn't be a lot of appetite for putting really anything of value in a rocket that, their boss says isn't going to work. And so rather than launching it empty or with just, a bunch of lead bricks in there as ballast, this is a cute PR move, I suppose.
Yeah. But I still think even at that long shot, there'd be some people who'd be willing to take a free flight to get their spacecraft on a Mars intercept trajectory. And I mean, it's a 2,000, I don't know what they weigh, a couple of thousand kilograms compared to...
Oh, yeah, the Falcon Heavy can launch like 40 tons into low Earth orbit.
Yeah,
so
and could send a chunk to Mars.
Yeah, their webpage says that although it wouldn't fit in the fairing, they could launch a fully loaded 737 into low Earth orbit on this rocket.
Yeah,
so that's pretty impressive.
So you took a 737, ground it up, and just sort of poured it into the fairing.
People and all. And it would, if it fit, it could go into space.
Wow. Well, so we're now at the whim once again of Elon Musk and the SpaceX folks to make this happen. So, Elon Musk, if you're watching, good luck.
Didn't work in 2016. Didn't work in 2017. 2018 is the year I'm feeling it.
Yeah, no, for sure. They're gonna, no matter what, that thing's gonna do something in the next couple of months. Something, probably explode. Paul, what are you looking forward to?
You want it to explode just out of the right end.
Yeah, right, in a controlled launch. Paul, what are you looking forward to?
Yeah, so I was thinking, because like you said, there's a ton of cool stuff coming up in rocketry and space launches. There's tons of solar system probes sent out there. But I was looking, what are some potentially exciting cosmology and astronomy developments that might be around the corner based on our current technologies, our current instruments, our current surveys that are in operation now? And there's two things that I think are going to become really big in 2018, or at least I hope are going to become really big. One is the epoch of reionization. So we were talking earlier about the James Webb Space Telescope, the hunt for the first stars and the first galaxies. You can actually hunt for the first stars and the first galaxies without hunting for the first stars and the first galaxies.
Whoa. Explain how.
Yeah. So, so what was the universe like before there were stars?
It was hot.
It was hot. It's kind of warmish.
Yeah. It was
was
I don't know,
pretty
big cloud
uniform,
of
I guess.
primordial hydrogen and helium.
Right. You had the primordial hydrogen and helium. And then you get the cosmic microwave background. What happens to the gas after the cosmic microwave background is formed?
It goes transparent.
It goes transparent. Yeah, it becomes neutral. Right? You get atoms. So you're all the hydrogen and helium in the universe becomes neutralized.
When did this turn into a test? Wait a minute.
This is now an exam. Welcome to the first day of classes. So you have a neutral gas, but if you look at all the gas and dust in the universe today, it's almost overwhelmingly ionized. All the gas in the galaxy, all the dust hanging around, that's all plasmas. That's all ionized gas. So something happened in the history of the universe to transform the gas from neutral to ionized. And we're pretty sure it's the first stars, the first galaxies, the first supernova, the first quasars. They emitted so much high power radiation that they ripped apart the neutral gas. So we know this epoch had to happen. We call it the epoch of reionization. And it is the last major uncharted territory in cosmology. We have a lot of maps and surveys of the present day universe. We have a lot of maps of the very early universe from the cosmic microwave background itself, but we don't have a lot of stuff in between.
Right. And so what is the tool? What are the methods that scientists are going to use to dig into this?
Right. So it just so happens that neutral hydrogen gas emits radio waves at a very, very, very specific frequency at 21 centimeters. So if you hold out your hands like yay big, 21 centimeters apart, neutral hydrogen gas emits radio waves at that wavelength. And so when the universe was very young and it was neutral, it was emitting a lot of this 21 centimeter radiation. Then as it became ionized from those first stars, from the first galaxies, from the first quasars, that went away. So you can map the transition from a neutral universe to an ionized plasma universe by looking at this 21 centimeter radiation, and that's firmly in the radio. So we have radio telescopes operating right now that are hunting for this transition point, that are hunting for the effects of the first stars forming and dying and blowing up and how it transforms the rest of the universe.
So we've had radio telescopes though for like 50 years. What makes 2018 the year that we actually that we actually do this?
Yeah, so this signal, the challenge with this signal is this signal that's primordial at 21 centimeters from the distant universe is incredibly tiny. And there are so many other sources of radio waves in our universe, like humans with their radios, from the solar wind to the galactic magnetic field, from nearby supernova. We are swamped in radio waves that are far, far stronger than this primordial signal. So we've had to build specially designed radio telescopes to go hunting for this very faint signal, and sophisticated analysis algorithms to actually pull that faint signal out of all that noise, out of all those foregrounds, to hunt for the cosmological signal. We now have instruments that are operating. So if you've heard of LOFAR, the low frequency array in the Netherlands, that's been hunting for the epoch of reionization for a few years now. There's HERA, the hydrogen epoch of reionization array in South Africa, which just got built last year. They're collecting data right now, and they're hunting for it. So it's just a matter of time of one of these instruments somewhere in the world that's hunting for this signal will get a clear detection, and will open up this era, this epoch of reionization, the dark ages, the cosmic dawn, probably in advance of when James Webb Space Telescope will be pinpointing individual galaxies at that same era.
So they don't have to launch it then.
Right. Exactly. It's in the ground. You just have to go to deserts, which are really quiet and far away from other people, and build a big giant radio array.
All right, so here's what I'm looking forward to. Not exactly looking forward to. Am keeping an eye on, and I actually just did an episode about this on the Guide to Space, and that is that the Chinese built Tiangong-1 space station, which has been up in orbit for several years now, but the Chinese lost control of it a few years ago, and have no ability to change its direction or attitude. There's no way to talk to it. I don't even know if they could deorbit it, but it has been slowly losing altitude, and now current calculations say that it's going to be coming down at some point, probably in mid-March. Now, the Chinese have released a map, but essentially if you're in kind of Northern California or south, and then maybe the very bottom of Australia and north, if you imagine the big band across the planet, it's going to fall somewhere in there. Who knows where and when. And so just, look up every now and then. Now,
could we shoot it down?
Well, the problem with shooting it down is, so it is definitely built pretty tough. And so when it does re-enter the Earth's atmosphere, chunks of it are going to make it through the atmosphere and they're going to hit the ground. And this happened with the Skylab was a fairly recent example of this back in the 1970s. And it was this, sort of where's it going to fall? Where's it going to fall? And it ended up smashing and landing in the Australian outback, a little to the east of Perth. So, and this has happened as well. There was I don't know if you guys remember, there was the URS spacecraft that came back to Earth about, half a decade ago. And there's been a couple of these. The Phobos Grunt did the same thing. Mm-hmm. Now, normally they're able to deorbit them, and there's this place in the Pacific Ocean they call the spacecraft cemetery, and they will deorbit them, and they put Mir down there. They put a lot of the Progress, the cargo ships that are attached to the space station. They deorbit them all into this gigantic swath of ocean where you're the farthest you can be from human civilization, and so it's about the safest place. And there's more than 100 spacecraft sitting down there in the ocean, but the problem is every now and then one of these space agencies loses control of their spacecraft, and then it just keeps moving through the Earth's atmosphere. It gets lower and lower, and eventually deorbits in a random location. Back in the day of the space station, it was, I think NASA calculated there was with Skylab like a 1 in 150 chance of it killing a human being. So I don't know, no one's worked out the odds on this one, nice. But maybe put it in sort of the same kind of thing. So not the chances of you getting hit are 1 in 150, but chance of somebody getting hit are 1 in 150. But nobody that we know has ever died to spaceflight debris so far. So Yet, yeah. So the chances
you just doomed someone.
Yeah, exactly. I didn't knock on any wood, but that would make me a bad skeptic.
So I'm surprised that this kind of spacecraft or the space station or something like this doesn't have some residual backup programming that if it doesn't receive instructions from Earth after a set amount of time, it has programming embedded in it to deorbit itself safely.
Well, it depends on what kind of capacity they had actually on board the station, right? So if they lost control of the station, maybe they were planning to send another of their capsules up to attach it, like the way that like with the International Space Station, they can control its attitude. They can control its height using the cargo vessels that are attached to it. They can use it with the Soyuz. They can use it with the Dragon, and there's some control on it as well. With this one, I guess they just didn't. They just lost control of it, and now it's out of control, and they can't. You can imagine things tumbling there, and so they just have no easy way to be able to dock to it, and no way to sort of do anything else, and they can't communicate with it. They can't stop it, so it's coming back.
Didn't this movie come out last year?
A couple of years ago.
Oh, okay.
Yeah. Well, normally, I mean, there's that sort of that idea of the Kessler Syndrome, right? Is that what it's called? Where you've got this sort of cloud of debris that's smashing into each other and creating more and more debris in space. But the thing is for the stuff that's so low altitude, it's all going to burn up or crash into Earth, but it's not going to be out in space anymore to cause future missions a problem. So
this is the big thing you're looking forward to in 2018?
This is the thing that I expect for many of the people watching this, this is going to be one of the first times that they will have heard of this or be thinking about it. And so this is the thing that I kind of wanted to put into people's brains, was just sort of when the news starts to ramp up, because I promise you it's going to be gigantic. Because it's like nobody knows where and when this thing is going to hit exactly. And so
it's going to be like the Chinese are bombing us from space type headlines.
Well, it's not even that. People are just going to be anxious about where and when this thing is going to return to Earth. So it most likely won't do anything, but it could smash into your house. If it does smash into your house, whatever you do, don't go near it, because there are potentially toxic chemicals on board that could be very dangerous.
Yeah, they just say that so that you don't
find the aliens.
See all the secrets.
Yeah.
I'm not buying that for a second.
But most likely it's going to crash into the Pacific Ocean. But back with the UARS, the UARS spacecraft, they had one of these tracking websites, and I was watching it, and it was coming directly towards my home. Was on the flight path as this spacecraft was going around on its final orbit, and it ended up probably going into the ocean thousands of kilometers to the west of me. But still, Aaron C is mentioning in the chat we should do a crash location pool. We did that for the last one on Universe Today, where we had people pick the place and time that the spacecraft would come down. I'm sure there's going to be, again, I think people are going to, you're going to see just the level of awareness ramp up and up and up. And so I think it will be, if something bad happens, it'll be the big story of the year. But I think right before it comes down, it's all you're going to be hearing about. And people are going to be watching it, people are going to be talking about it, and you're going to be tracking it. So I think it's going to be, more attention is going to be paid to this space story than anything else for most of the year, I think. I'm calling it now.
You're calling it?
I've been through it. I'm a grizzled veteran. I've been through two of these. Yeah, for sure. All right, Morgan, what have you got?
We'll see. I think other things. I bet when we do a recap of 2018, I don't think we're even going to mention it.
Really?
I think it'll be big in the moment.
Yeah.
And then we're going to move on, and we're not even going to remember.
Well, the thing that's funny was I went back and checked the recap show that we did, and 7 out of the 10 were surprises.
Nice.
So I wouldn't be surprised if, we'll get about the same ratio, that there's going to be 7 things that happen in space this year that are complete and total surprises. And we know we're going to put the launch of the Falcon Heavy on there and a couple of other things for sure. So,
Morgan, even if the Falcon Heavy blows up?
Well, then it gets to be number 1 story. Either way, I think it'll be one of the top stories, unless, we see some kind of like super kilonova, maybe.
That's just a supernova. You're just back to supernova.
like a really powerful kilonova.
Excellent nova.
Yeah, a mega nova. Is that taken yet? Would that be next after a kilonova, a mega nova?
No, I think a supernova is a meganova, right? 1,000,000 times brighter than a nova.
That's bad notation right there.
Yeah, a giganova.
Well, I'm not in charge of names.
No,
okay?
but I think we need, because there's so many different kinds of supernovae, shouldn't we switch to like giganova, meganova?
Well,
right? Exanova.
All the nova are now called cataclysmic variables. But supernovas still get to be their own supernova. You can thank Fritz Zwicky for that notation.
All right, I'm trying hard to do this. Morgan, what's next?
I'm going to take Kimberly's story, which is the launch of Tess. And I've been sitting here trying to come up with the acronym for Tess. It's Transiting Exoplanet Survey...
Something.
Satellite?
There's 2 S's. Maybe that's it. But the idea here is to take Kepler, which use the transit method to find a ton of stars in one small part of the sky and cover the entire sky with that, but at a lower level. And a number of surveys here on Earth have realized that you don't need really high precision measurements like Kepler made if your stars are really bright. And what they've done basically is they've taken camera sensors and they've put spherical lenses on them to look at huge swaths of the sky. And they just take tons and tons of data. And then they run all of that through an algorithm that can beat down the errors and the noise in it until you can find the exoplanets. And with Tess, we're going to do that for all of the local stars. So all of the stars out to like 100 light years or something in the whole sky, we're going to check for exoplanets with Tess. And this will provide us with numerous targets that are going to be the ideal follow-up targets for things like James Webb. The problem with a lot of the Kepler systems is they could be really fascinating systems, but they were really far away, and so it's hard to look for an atmosphere or something. But by its nature, Tess is only looking at bright nearby stars, and these are going to be the best stars to observe from the ground and from space once we find interesting systems around them.
I think Tess is going to find Earth 2.0. It's going to find the Earth-like planet orbiting a sun-like star within the habitable zone. This thing that we still haven't found yet, thanks to Kepler, and it's not enough gyros. So
right, it's a numbers game, though, right? It's limiting its search volume, so to speak. It's going to have fewer targets than something like Kepler. Its targets will be juicier, so if it gets it right, we have a lot more opportunities, like Morgan said, for follow-up. But if Earth-like planets around sun-like stars in the right orbits are relatively rare, it's going to have a harder time finding those.
Yeah, I mean, at this point, with the number of close calls, I mean, with the number of stuff that's being found at red dwarf stars, it feels like it's just, we just didn't have the right tool to be able to sense it enough to find these Earth-sized worlds around these sun-like stars. They found lots of planets around sun-like stars, and they found things. They just haven't found the Earth-sized worlds yet. So I think this feels like it. Assuming it's got enough, gyros, then we're going to be all right.
One side effect of Tess is it's going to sort of be killing the dreams of young astronomers all over the place. Because, since Kepler, basically, you could grab any old, small university telescope and point it at a random star and start making observations. And, you'd have a 1 in 10 chance of finding an exoplanet. And so all of these sort of small-time amateur observers all over the world have been adding to our catalog of exoplanets by just looking at random stars and checking, hey, does this one have an exoplanet? And Tess is going to just wipe that out because they're going to find all of those exoplanets
all of them.
Around all of the stars that you can expect to see with a small telescope.
Yeah. Yeah. But still pretty exciting. And so that's launching this year. All right. Now, Paul, you weren't prepared for this, but I figure you can handle it. We should be getting the first image from the Event Horizon telescope this year, right?
That's right. I totally forgot about the Event Horizon telescope. It's been collecting data for 6 months now, since they had first light, I want to say. So there's, of course, kinks to work out and analysis algorithms to shake down, and they're expected to have enough data, enough good data, that they can produce a reliable image of the stuff right up against the event horizon of Sagittarius A star, which will be neat.
Yeah. And unless the picture sucks, it's going to be one of the big stories of the year.
Well, it is going to suck.
Yeah,
it's going to be blobby and blurry, and then there'll be a hole in the middle. Or probably not, because the dust will still obscure the front, but it'll be like the stuff right outside of it. And so we'll be talking all about it. We'll be on the news and everything, showing people a blurry, blobby thing. And everyone's going to say, gosh, these astronomers, they get excited over everything. And then some, they'll commission an artist to do the artist impression, and then that's the one that we're all going to point to.
But that'll be pointless because the whole point of this, I mean, people can artist illustrate what black holes look like. I guess we haven't seen the event horizon for the first time, but the whole point is to get that first photograph of it, and by photograph I mean radio telescope scan, but still.
So is Sagittarius star the only source that this telescope is supposed to observe? Is it just like a one-trick pony?
No, maybe Andromeda as well. So a two-trick pony. But, you know, it's a worldwide collection of radio telescopes that have all been directed to one job. So it's not like someone launched a satellite that has this one purpose. These are radio telescopes. They just happen to be collected around the whole planet.
But these are the only things we'll be able to use this basic technique for.
Yeah, it's not like a solar telescope.
Nearby ones.
Right? Like, what else you can use the solar telescope for?
If I remember right, and I'm not 100% sure, a lot of the telescopes that are participating in the Event Horizon Telescope are general purpose radio instruments. And I think a part of their time collectively is being dedicated to this joint interferometric observation of Sagittarius A star. So I think all these instruments already exist. They're already doing tons of science. They're just being coordinated together to provide.
They need a new, less confusing name for it then. I was imagining some cool new telescope that was just staring at a black hole all day.
It is a cool new telescope, Morgan, because it's a network of smaller telescopes all around the globe coordinating their efforts.
Yeah, they've turned all of the large radio telescopes of planet Earth into one big telescope. How cool is that? And they're doing interferometry on it after the fact, which is also very complicated and awesome. And in fact,
that sounds heinously hard to do interferometry across all those different systems.
With radio telescopes, it's the easiest thing you can do this with. The only way you can do this, really.
Yeah, but still, that just seems, all the timing involved in that seems horrible.
Yeah, so if you've looked at VLBI, the very long baseline interferometer, that's a lower scale version of what this is. Multiple instruments across the globe, including a satellite or two, combined together for image synthesis using interferometry. This is just like the next level up.
The thing that I love about this is that the delay is happening. Part of the delay is happening is because one of the telescopes involved in this is located in Antarctica, and they're having to they can't get the data out of Antarctica. They can't get it out by satellite. It's too much data. So they have to get physically out of Antarctica, and they can't do that until you get into the Antarctic summer, when you can actually start making flights happen again. And that only has opened up, we're in the Antarctic summer now, but, and so they had to wait. And so all of the other telescopes, they took the image back 6 months ago. But now the data is being assembled and mashed together and merged. And so hopefully we'll find out shortly. All right, I've got I got two actually quick things that people should be looking forward to this year. One is we're going to have a Mars opposition, which is going to be, and I don't have the exact date actually. Let me just pull it up. We're going to have a Mars opposition this year. And it's going to be almost as good as the one that we had back in 2003. So that's going to be a good one. July. So 26th of July, we're going to have a really bright Mars approach. And I don't know if do you guys remember the 2003 Mars?
I do remember the 03.
It was obviously it was amazing, right? Like just this guy was on fire.
Yeah, I was actually.
I don't remember it.
The Poly Observatory back in the day. I was the manager, and we would point our telescope at it.
Yeah.
Because it was big.
Yeah, it was so bright. Like Mars was just blazing in the sky, and so hopefully we'll get another one of. It's not going to be quite as.
Does it get brighter than Venus when it's that close?
Nothing ever gets brighter than Venus.
Okay.
But it sure looks stunningly bright. So yeah, it's pretty amazing. And then the other thing that we should be mentioning is the Parker Solar Probe is going to be launching in summer, and this is of course NASA's mission to visit the sun.
Which I feel like I'm in the Twilight Zone because I feel like it was already launched. I have no idea what's happening to my brain.
It's going to launch. July 31st on a Delta IV Heavy. And then it's going to do a bunch of flybys. It's going to do a flyby of Venus on September 28th. It's going to do a flyby again of Venus on December 21st. Another flyby of Venus on in 2020, and then another one, and then two more in 2021, another one in 2023, and then another one in 2024. And it's going to have to do all of those flybys of Venus to get gravitational slingshots to be able to get it into an orbit that is ludicrously close to the sun.
So do you think that if their instruments are, like shielded to stare at the sun, do you think that Venus is just invisible to it? Like you point the camera at Venus and it just can't see anything because it's not a billion times brighter than a planet.
Yeah, so it's got a shield. It's amazing. It's got a I forget the exact amount. It's got several centimeters of just shielding that it's going to face towards the sun as it's doing its flyby while it tries to gather some data and instruments. And so it's going to be, and I forget the exact perihelion is, but it's going to be ludicrous. Okay, here you go. 6 million kilometers from the sun.
It's like 5 or 6 solar radii.
Yeah, the sun is
it's like stupidly close.
1.4 million kilometers, I believe, and so it's, as you said, it's going to be about 4 solar radii away from about 6 solar radii, away from the surface of the sun. It's going to be experiencing thousands of Kelvin in temperature, and then we'll zip back out into this big long orbit. So it's the sun is the hardest place to get to in the entire solar system, and so this is
you just drop things.
Yeah, you just let go. The problem is you have to cancel out the 30 kilometers per second of orbital velocity that you've got thanks to the Earth. So it's actually a tremendous engineering accomplishment, and to be able to do this, and they couldn't do this without more than a half dozen Venus flybys. So it's going to be amazing. But we're really not going to get that payoff for another 2024. We're going to get the first really close approach to the sun. It's going to do
Horizons do its flyby.
Yeah, so it's going to do
1 year from now.
Yeah, it's going to do a couple of perihelion approaches every year and just get closer and closer and closer and take better and better data. But come 2024.
New Horizons is January 1st, 2019.
Next year.
Okay, so we'll have to do it in. We can't talk about it now.
No, we're gonna have to wait till next year. All right, well now it's time for our interview. There's our interview, and we're back. All right, well, it's time to wrap things up. Before we do, we have no clever way to end this show. Could you guys endorse a thing? How about that? Morgan, have you got a TV show, movie, book, video game, anything you've been trying out recently that maybe people would dig?
Yeah, we just finished watching season 2 of The Crown, about the Crown and Queen Elizabeth, and it was just as good as season 1, and I'll be sad to see those actors go and new ones appear.
You got a Switch too, right?
I did get a Switch. I'm a little late to the game on the Switch front, but I have been playing the heck out of Super Mario Odyssey. And guess what? Nintendo makes good video games. News at 11.
Paul?
I am behind the times. I finally binge watched The People versus OJ Simpson, and I'm not going to spoil it for you, but it is a nail biter.
How does it turn out?
I'm not going to say. You think it's going to go one way and then maybe the other. Oh, man.
All right. And for me, I've, of course, have been watching Black Mirror. The latest season dropped on the 29th, and we binged them in one day. As usual, kind of a mixed collection of episodes. The first one, though, is absolutely terrific. I really, really enjoyed it. The second one was really good. There's like a robot one that I thought was really great. One's kind of sappy. A lot of people liked it. I wasn't too crazy about it, but yeah, it was a solid season. So, Black Mirror, if you haven't caught up to all the Black Mirror episodes. All right, Paul, where do people find out more?
they can go to my website, pmsutter.com. That's pmsutter.com. And there's links from there to my podcast, Ask a Spaceman, my radio show, Space Radio, astrotours.co for trips around the world, and all my writing, everything, and pictures of me, if you're into that.
1 month and we're off to Iceland.
I know, right?
Yeah. Yep. Morgan, where do people find out more?
God, I feel like I need a whole list of websites like
really
Paul
do.
has. I'm just going to need to make morganrenberg2.com, morganrenberg3.com. But for now, you'll be stuck with morganrenberg.com, where you can swing by the Fort Worth Museum of Science and History and say hi.
Right on. I put up the wrong lower third there for a second. I apologize to everybody. Right, of course, you can see all my stuff over on YouTube, on Universe Today. Check out what we're doing on Instagram. Lots of good stuff. All right, I'm going to switch us to the gallery view. There's all of us. Let's say goodbye. Thanks, everyone. Thanks for joining us for that last trip around the sun. Here's to another great trip around the sun. Thanks, everybody.